recording. All right. Before we get going, just a couple of housekeeping notes. The first thing is that RA is available for tutoring until 4 o'clock. And then, let's see. Yesterday, I sent you guys out an email with what I call the sort of home stretch schedule. We've only got about a little less than a month left in this class. And so I kind of laid out everything for the rest of the semester, what we're going to talk about on each class day, what sections of the textbook they're going to come from, also, what projects you're going to get when they're due and what the assignments are. A couple of things here are, even though we are going to dip into Unit 13, and it will be on the exams, we're not going to do a self-study assignment for Unit 13, so you just have to sort of study that one the old-fashioned way, read the book, memorize the stuff, call it good. You've got a project assigned today. It's due a week from today at midnight. We'll talk about the details for that in just a second. There are 2 exams left. The last midterm exam will be here on November the 23rd. It's the Monday before we leave for Thanksgiving break. And we're going to, in keeping with our sort of constant way to try to figure out what method works best in our environment, this exam and the final exam will both be multiple choice exams. The first midterm, midterm 3 here will be a 50-minute exam. You'll take it in Blackboard. It'll be multiple choice questions, open book, open note, open internet, but I'm going to write you 65 questions for the 50-minute exam. Basically, I'm going for about 45 seconds per question. The idea here is that, you should have obviously studied and know the material, and that way when you come to a question, you should be able to just answer it or not be able to answer it, and there really isn't a lot of time to do things like post them on Chegg or anything like that. And the test will be available from 8 o'clock to 11:59 p.m., and it will cover all of the material that we cover from today through November the 18th, and then on the 20th, that Friday before the exam, we'll do a review session for midterm exam 3, and I'll write a review for the exam. Any questions about that? I see Liam typing some stuff. So I think you can. There are pros and cons to it being a multiple choice exam, right? So there won't be any deep dive circuit design questions, no open-ended design questions. So the questions, while there'll be a lot of them, will arguably be easier. There'll be little bits and pieces here and there. We'll try to work in some circuit design stuff. But again, because there's not a whole lot of time, it'll be really just, do you understand the concepts? Do you understand the behavior of the devices that we're talking about in class? The philosophy there is, I'm going to use the 3 exams that we're going to do the 3 projects over the next month. That'll be where we figure out if you can, design a circuit and actually implement it. The tests are, do you understand the concepts? Do you understand the vocab? That kind of stuff. So that's really the sort of difference there. The exams, and I'm going to build on this for next semester's class. That doesn't affect you guys, but the idea is there. The exams are going to test what you know, and the projects are going to test what you can do. So that's my philosophy there. Any other questions about this? Mostly based on textbook. Yeah, straight out of the textbook and straight out of the lecture slides that we're going to use for the rest of this class. So pretty standard. That'll be pretty standard issue college test, right? Read, memorize the facts, know the vocab, get asked questions, answer the questions, right? And I'll try to sprinkle in some practice questions and stuff throughout the lectures so that you kind of get a sense of the style of questions that we're going to ask. So yeah. Oh, last thing is the December 4th will be the final exam. Even though for this class in particular, I think our exam date is given as December the 9th. It will not be on December the 9th. It'll be on December the 4th, right? Since we're a hybrid class, I have the flexibility to assign it whenever I want. So we're going to do it on the 4th, which is the first day of the final exams, but it'll be available from 8 a.m. till midnight. Same format as midterm exam 3. It'll be multiple choice questions, but here it'll be a 100-minute exam with 130 questions, and we'll cover the entire course. We'll spend the 2 days that we get back from Thanksgiving, Monday and that Wednesday, reviewing all of the key material, the stuff that I'm going to put on the exam. We'll review on these 2 days. see people are typing. Is the final exam going to be over Unit 1 to Unit 9? No, it'll be over everything. So it'll be over Units 1 through 5, then 7 through 9, and then 11 and 12, right? So it'll be everything that we've talked about in the class. Let's see. And yes, I forgot to mention, the final exam is optional and will replace your lowest exam grade. Now, however, there is no, if the final exam is your lowest test grade, then nothing will change, right? So there's no risk to taking the final exam, right? And that works out just fine because since everything it's multiple choice, it's graded automatically in Blackboard. There's no like extra work. Like Max doesn't have to grade the final exams, so there's no harm in having you take the exam. So you can give it a shot, and hopefully you'll do better, and it'll bring your overall exam grade up a little bit. So yeah, so it's optional. You don't have to take it if you don't want to, but it will replace your lowest exam grade. I guess another way to think of it is we have 4 exams, 3 midterms, and a final, and we're going to replace the lowest of those 4. Wait for Adrian. Adrian asks, what will that replacement grade be reflected immediately after completion? No, because we have to do that. Blackboard, I can't tell Blackboard to drop your lowest exam grade. It doesn't quite work that way. So no, after the exams are done, I'll export everything to Excel spreadsheets, and then I'll do those the same thing for the curve, right? So I'll need to put those all in Excel spreadsheets, and then do stuff like drop your lowest exam grade and add the curve and stuff like that. So no, so it won't happen immediately, because we have to do that manually. Blackboard doesn't have a mechanism for that. It'd be cool if it did. It'd be cool if I could like automatically put in a curve and automatically say drop the lowest of these grades and stuff like that. All right, people are still typing questions. So yes, Adrian asks, so the test average will consist of 3 exams? Yes. So there are 4 exams, 3 midterms, and a final. That'll be the best 3 out of 4. Will a copy of the schedule be available on Blackboard? I ought to put it on Blackboard. I emailed it out to everybody, so you should have a copy. Aaron's telegraphing that he doesn't check his emails from me. But now I'll go ahead and put it up on Blackboard too. All right. Any other questions about the schedule or the tests? Okay. Let's talk about the project. You got a project due today, or that is assigned today. It's due 1 week from today. Let's go over that real fast. It's combinational logic design, and here's what you've got to do. I'll go ahead and come back to the instructions here in a second, but here's the description. Implement a Verilog module to realize a logic circuit to the following specifications. Take as data inputs 2 4-bit 2's complement binary numbers, right? So this means 2 4-bit numbers that can be positive or negative. They're going to be A and B, as well as a single 1-bit control input C. There should be a single 4-bit output Y, which is also a 2's complement binary number. The value of Y should be equal to the sum A plus B if C is equal to 0, and the difference A minus B if C is equal to 1. I'll give you a test bench that you can use to verify whether or not your circuit is working, and you don't need to worry about any overflow conditions. If you don't like that sort of word problem style here, here's a little bit more of a concise summary. I want you to name your module top. Top is a lot like main in other programming languages. Like, so in C++, you would have like a main function. The top Verilog module is sort of like Verilog's version of main. So top with parameters A, B, C, and Y. It's got 2 data inputs A and B. Each of them are 4 bits. A control input C, and then a 4-bit output Y, which is equal to A plus B if C is equal to 0, or A minus B if C is equal to 1. are there any questions about the structure here? No. So Liam asks, should the file name also be top? No. If you come up here to the instructions, I want you to name your file your last name underscore your first name .v, just so we can track your stuff. So that's an important thing. Your Verilog module in your code will have top, but your file should be last name underscore first name .v. That way we know whose file is whose. And then, like I said, along with that, you'll be given, I've attached this test bench to Blackboard. So this is the same test bench that Max is going to use to grade your projects. Basically, the only thing you'll need to change here is obviously change the include statement to be, last name underscore first name .v, so it works for your thing. So we've got a top module as our unit under test. And then I just run through, there's 9 inputs, which means 512 test cases. So it just runs through all of them and makes sure that you passed all the test cases. And then it scores you out of 512. So, and you've got this test bench. So honestly, really, there's no excuse for you to not have to get 100 on these projects, since you have the test bench that will be used to grade your assignment. So that's the test bench. What questions do you guys have about this project? No questions about the project? All right, in that case, let's move on and have class. Don't forget, that's due you're going to submit just your .v file, nothing else, just your one .v file by 11:59 on Monday, 1 week from today. All right. So let's talk about what we're going to talk about today. All right. So we're going to talk today about SR and gated latches. And actually, we'll probably just talk about SR latches today. We'll get into gated latches on Wednesday, along with the other material, because we spent about 15 minutes here talking about the schedule and the project and stuff like that. So in the morning section, we only got through about the first 2/3 of this lecture. So our objective for today is in this lesson, you will characterize the operation of latch circuits. We'll talk about what latch circuits are by deriving their characteristic equations. So for every type of latch circuit, there's an equation that comes along with it, and we're going to talk about what that is. So kind of an overview of what we're going to do today. We're going to talk about feedback in switching circuits. Remember, a switching circuit is just a logic circuit, AND gates and OR gates, and all of that stuff. We'll talk about set reset latches. We'll talk about how to derive the characteristic equations for a latch circuit. If we have time today, we'll get into gated latches. And there we go. So that's what we're going to talk about today. So let's talk about feedback in switching circuits. Sequential switching circuits. So far this entire semester, since we've been talking about logic circuit design, we've been talking about what's called combinational logic, which is a circuit that just has inputs and outputs, right? You build the logic circuit, you give it inputs, it spits out outputs, and there's really nothing else more sophisticated than that happens. A sequential circuit is a switching circuit in which the output not only depends on the present input, but also on the past sequence of inputs. These circuits must also be able to remember the history of inputs to produce the present output. So these circuits need to have memory, and to make them work, we need to create memory devices, right? These are devices, logic circuits that can remember what the sort of past was. Yeah, I'm recording. Thanks for reminding me, Liam. So we need to create memory devices. And to do that, we're going to use latches, and then next time we'll talk about flip-flops. Latches and flip-flops are commonly used memory devices. Probably every other type of memory at its core consists of latches and flip-flop logic devices. They can assume one of two stable output states, from multiple inputs, and this is because they're binary circuits, right? The output states are still going to be just 0 or 1, no matter what the circuit is, right? At the end of the day, a single latch or a single flip-flop circuit will still only store 1 bit of information. So they can assume 1 of 2 stable output states from multiple inputs. Before we're talking about latches, let's talk about a really simple example and ask what might happen if we connect the output of an inverter to its input. Which is to say, what if we did this? We took a NOT gate, took an inverter, here we'll just call it X, and if we just directly tied the output back around to the input using feedback. And by definition, we're going to call feedback is when the output of one gate is connected back to the input of another gate in the circuit to form a closed loop. So when we have a loop from output back around to input, we call that a feedback loop. And here we have it, a feedback loop from the output of a NOT gate to its input. So take a moment and kind of think about what behavior are you going to expect to see from this circuit. If you were going to take a look at the output X, what would it look like in this case? Liam asks, does the gate have a delay? Yeah, the gate does have a delay. And Isman says, 0, 1, 0, 1, 0, 1. You're absolutely correct, right? All logic gates have some kind of propagation delay, as we saw a couple weeks ago. So if we kind of game it out, here's what we're going to have, right? Choose 1 or 0 to be the present state of the inverter. Remember, the inverter has to be in some state. And it doesn't matter which one we choose, so let's pick 0 to start with. After some propagation delay, that 0 arrives at the input. And then the inverter switches to 1. And then, after some propagation delay, the 1 arrives at the input. And the inverter switches to 0. And this process will continue forever and forever and forever. 0 to 1, 0 to 1, 0 to 1, 1 to 0, so on and so forth. So we get a waveform, we get a timing diagram that looks like this, right? Where we have, it starts at 0, and then it triggers to 1, and then it waits, and then it goes back to 0, and then it waits, and it goes to 1. And it's going to do that forever and ever, right? And this type of circuit is called an oscillator. An oscillator is a circuit which continuously toggles between states. And I probably ought to have expanded on that definition and said an oscillator is a circuit that toggles between states by itself, right? For other circuits, we can give it inputs and have those inputs cause the state to toggle continuously. But an oscillator is a circuit where, just like this inverter with a feedback loop, if we just take our hands off of it, it's going to switch itself between these two states. Right? An oscillator, the state of an oscillator is always what we're going to call unstable. So, are there any questions about this sort of inverting oscillator example? Right, the important thing is that we have a feedback loop, and the state is unstable. It oscillates between 0 and 1 without us doing anything to it. Next, we sort of alluded to unstable states, so let's first have a definition for a stable state. A stable state is defined here as when the feedback provides a signal which will not result in a change of state. So if a loop comes back around and it doesn't change the state, and that state is going to stay the same forever until we do something to it, that is a stable state. A sort of kind of boring example here would be if we had 2 inverters connected in series with a feedback loop coming around. So on this first example, if we have a 0, right, after some delay, that's going to become a 1, and that's going to pass to the next inverter, right? So that 1 is going to become a 0, which means a 0 comes back around, and so there's still a 0 on the input, so nothing will change. Same thing for the second example. 1 becomes 0, 0 passes to the next inverter and becomes 1 again, and so we still have a 1 on the input. So this circuit, while it's not very interesting and doesn't really do anything useful, is considered stable. Its state will never change. Now, of course, if you were to add 3 inverters in series, then you would be unstable again, and once again, you would have an oscillator. And in fact, you can build an oscillator by having any odd number of inverters connected in series. Isman asks, will that be equal to just 1 buffer? Yes and no. Yes, in that the logic behavior will be the same, but remember that the propagation delay matters, right? So you still have the propagation delay of the first gate and then the second gate, so it will have double the propagation delay. of the single inverter, right? So the timing will be different since you're passing between two logic gates. That's a good question, though. Okay, so now that we've got this sort of concept of stable state versus unstable state hashed out, let's talk about what we wanted to talk about, which are set, reset, or SR latches. So we can construct a simple latch by introducing a feedback loop in a two-level NOR gate circuit. So a circuit that looks like this. We've got two NOR gates. This first NOR gate has an input that we're going to call S, and then it has an output, which we label as P, that passes to a second NOR gate. That NOR gate has another input, R, and then it has an output, Q. And then that output, Q, forms a feedback loop that comes around to back to that first NOR gate. And so in this first example, we have S and R both equal to 0, and Q is equal to 0. So if we come back around to the input of this first NOR gate, we have a 0 and a 0, which 0 and 0 in a NOR gate will produce a 1 on the output. So we have 1 and 0. And a 1 on any input of a NOR gate is going to cause the output to go to 0. So Q is still at 0. And so our system, our circuit is in a stable state. The Q output is equal to 0, and it's not going to change. But what we want to do is look at what happens if we manipulate S and R. How does that affect that Q output? So let's take a look at SR latch operation. So here we started with S equals 1 and R equals 0. And so let's kind of trace what happens through here, right? So if S is equal to 1, right, we're going to have, remember, if we have a 1 input to any NOR gate, we will automatically have a 0 on the output. So we have a 0 and a 0, since R is equal to 0, on the input of the second NOR gate, which will produce a 1 at Q. And that 1 propagates back around and here and goes to the input of the first NOR gate. So we have 1 and 1, and 1 and 1 on the NOR gate will produce a 0, which produces a 1 at Q. So that 1 at Q output is stable. So when we set S, which stands for set, so S is set, R is reset. When S is equal to 1, then Q is 1 and is stable. Now what happens if we bring S back to 0, right? So S was equal to 0, R is equal to 0, but remember that Q was equal to 1, right? So we went S and R were both 0, then we did S equals 1 and R equals 0, then we brought S back down to 0. So this Q is equal to 1. So if we bring the feedback loop around, we'll have a 1 and a 0 at the NOR gate, which produces a 0 at the output P. 0 and 0 on the second NOR gate give us a 1 at Q. So that's the magic here, right? So it stays at Q stays at 1, right? Even though we started by saying S equals 1, R equals 0, Q went to 1, and then when we brought it back to 0, even though the inputs changed, the Q state stayed exactly the same. So it remembered the state that it was in before, right? We set it with a 1, and then we went back to 0. 0 for the SR latch is like the resting state, right? Nothing changes when it's 0, 0. But it remembers what it was before. And now, by that same token, if I say, let's make R equals 0, so let's set reset equal to 1, excuse me, I should say R equals 1, and S equals 0, right? Then we have a 1 on the second NOR gate, right? And a 1 on the input of any NOR gate means it's going to go to 0 no matter what. So Q automatically is driven to 0. Feedback loop comes back around. We have 0, 0 on the first NOR gate, which gives us a 1 at P. So we have 1, 1 on the second NOR gate, and Q is now still at 0. So by setting 1 on R, then Q is 0 and is stable right there. And then if we return back to our resting input, 0 and 0, with Q equals 0, we're going to have the same stuff, right? We're going to have 0, 0 on the first NOR gate gives us a 1. 1, 0 on the second NOR gate gives us a 0. So we return to 0, 0, but the state remains Q equals 0. So that's the punchline there, right? When S goes to 1, Q goes to 1, and then when we return to 0, Q will stay at 1 until we say R equals 1, and then Q will go to 0. And then when we go back to 0, 0, Q will stay at 0. Q remembers which one of these was 1 last. Now, we've drawn our SR latch in this way to kind of keep it consistent with that inverting example that we saw. But oftentimes, SR latches are drawn in what's called cross-coupled form, with a Q and a Q prime output. So we get a circuit that looks like this. We still have R and S as our inputs, but now we have Q and Q prime as our outputs. And if you were to go ahead and trace this logic circuit, you'll see it behaves kind of exactly the same, right? S feeds to the first one, which then turns around and feeds the second NOR gate here with R, and the output is Q. But the only thing is that our P became Q prime. So a lot of times you'll see Q prime and P used interchangeably. But this is a much more popular way of drawing our set reset latch, right? And then if you don't want to draw these logic gates, a lot of times you'll see just a box with an L in it for latch, with inputs R and S and outputs Q prime and Q. Now we talked about 3 different cases, right? We talked about, when S is equal to 1 and R is equal to 0. We talked about when R and S are both equal to 0. And we talked about when R is equal to 1 and S is equal to 0. But we've left out one case, the case where S is equal to R and they're equal to 1, where S and R are both equal to 1 is bad, right? So we say that the case where S equals R equals 1 should never be allowed. It's going to cause all kinds of problems. When you do set S and R both equal to 1, this leads to unpredictable behavior. There's all kinds of things that can happen. So for example, if we set S and R both equal to 1, remember that will drive the outputs P and Q to both be 0. So remember, 1 at any input of a NOR gate gives you 0 on the output. So we'll have P and Q both be equal to 0. But if we drive them both back to 0 simultaneously, what happens then is we get a 1 here and a 1 here, which should drive the output to 0. And this will happen sort of constantly, right? In fact, if you start S and R both at 1 and drive them both to 0 simultaneously, you will cause the SR latch to start to oscillate, just like our inverting feedback loop did. It'll go from 0 to 1 to 0 to 1 to 0 to 1, so on and so forth. And that's not good. You don't want a device that's supposed to just store the value of a single bit shouldn't oscillate. Also in practice, what this means is, the oscillation will only happen if both of these gates have the exact same propagation delay. But often, in fact, almost always, that's not the case, right? There'll be a slight difference in propagation delay between the 2 logic gates. So what that means is that the latch will fall into one state or the other, but it's impossible to predict which one it will fall into. So that's why we say it has unpredictable behavior. And unpredictable behavior in memory devices is always a bad thing. So you never want to set 1 and 1 on the inputs of an SR latch. Always just have them be the complements of each other or be 0. All right. Any questions about the behavior of the SR latch? Can you stop the oscillation if you do accidentally cause it? Yeah, so if you were to change, say, like S back to 1, then it would stop oscillating. So yeah, so you can stop it if it starts. And like I said, the bad thing is not that the oscillation starts, because in practice, in a physical circuit, the oscillation almost never will happen because the propagation delays will almost always not be exactly the same. There'll be a few nanoseconds different. But you're never going to be able to predict the output that you're going to get, right? And the whole goal here is to control our circuits. Unpredictable output is bad. But yes, you could stop an oscillation if you started it by accident. Okay, let's quickly look at a timing diagram for the SR latch. And it's basically what we expect. If everything starts at 0, then Q, everything starts at 0, so we say Q is in the initial state 0. Then when S goes to 1 at time T1, there will be some little bit of a delay that we use epsilon to represent, some little tiny delay before Q also triggers to 1. And then when S goes to 0 at time t2, Q will stay the same. Q will remember that it was in the set state until t3 when R goes to 1. So now we're in the reset state, which means that Q will go to 0, but it won't go to 0 until some tiny propagation delay time after time t3. And then, of course, at t4, when R goes back to 0, Q will stay in the state 0. So we go from one state to the other, but there is a little bit of a delay from when you trigger them. And so it's important because the duration of the state change in S, right? However, the length of this pulse from 0 to 1 and then back to 0 has to be greater than this delay. If this pulse is smaller than this delay, then the state will never change, right? And you will have some problems because you will have thought that you put it into a state and you didn't actually. So you have to make sure that your pulse is longer than the propagation than the propagation delay of Q. Because if you don't do that, it leads to what we call a metastable state, which is, we talked about unstable states, meaning that the circuit oscillates continuously. A stable state is where the state stays the same. It's either a 0 or a 1, and it's not going to change until we apply some input to it. A metastable state is an unpredictable state. Officially, we define it here as when the voltage level at the output of the circuit is approximately halfway between the voltage levels for a logic 1 and a logic 0. When it's weirdly somewhere in between the states, we call it metastable. And it will eventually fall into one state or the other, but its behavior is unpredictable. And then there are several cases that can lead to a metastable state. I want you guys to know two of them on the exam. The first one is the one that we already talked about, the simultaneous switch from 1 to 0 in S and R. So when S and R are both equal to 1, and you switch them both to 0, that puts the circuit into a metastable state where the output is going to be unpredictable. Right? It could also lead to an unstable state. It could lead to oscillations, but most likely it's going to lead to a metastable state where the output state is unpredictable. And also, if you have Q equal to 0 and a pulse on S with a duration that is approximately equal to the propagation delay in Q. So for example, if I go back here to our timing diagram, right, we have this propagation delay epsilon at Q, and we said if the pulse is longer than epsilon, then we're going to get a state change. If the pulse is less than epsilon, then we won't get a state change. But if S is equal to epsilon, then anything could happen. It's a coin flip to see what might happen, and we call that a metastable state. So those are our two cases that you need to be aware of for a metastable state: a simultaneous switch from 1 to 0 in S and R, and starting with a Q equals 0, a pulse in S with a duration that approximately equal to the propagation delay in Q. So a pulse that is the same length as epsilon. Any questions about the metastable state? Okay. All right, moving on. Now let's talk about deriving the characteristic equation of our latch circuit. The first thing we need to do is define what we call present versus next state. The present state is defined as the state of the Q output of the latch or the flip-flop at the time any input signal changes. So whatever Q is when we change an input, that is the present state. And then the next state is the state of Q output after the latch or flip-flop has reacted to the input change and stabilized. So we changed an input, the latch or the flip-flop does whatever it's going to do, and then it rests in a state. Whatever that state it ends up in that is stable is the next state. So using that, we can define our characteristic equations. A characteristic equation, also called the next state equation, is an equation that expresses the next state of a latch in terms of its present state and inputs. It's the Boolean function, but the sort of function is not only dependent on the inputs, but also dependent on whatever the present state is. Yeah, let's see. There you go. Awesome. All right. So if we're looking at a circuit like this, right, this two-level NOR gate circuit, our SR latch, we've got inputs S and R, and we've got P and Q. And we're going to focus on Q as the state of our latch. So let's leave that diagram there. And let's say that we want to have Q as a function of time. So Q of T represents the present state. So Q right now, at the moment our input changes, coming back to that timing diagram. And then Q of T plus epsilon represents the next state. Now don't let this sort of time function notation freak you out. It's still going to be a Boolean expression, just like normal. So Qt is the present state, and Q of T plus epsilon is the next state. So here's our characteristic equation, right? If you were to go through and sort of trace this out using the Boolean algebra techniques that you already know, you would find that Q of T plus epsilon is equal to R of T prime and S of T or Q of T. So like I said, I know that we've sort of thrown this of T notation, this regular sort of mathematical notation in here, but don't get freaked out. It's still just a Boolean expression. In fact, in a little bit, we'll simplify it so it really does just look like a Boolean expression. We can apply the distributive property and just get this, R of T prime and S of T, or R of T prime and Q of T. So that's our Boolean expression, our characteristic equation for this latch. We can derive a similar equation for P, and P is just the application of De Morgan's theorem to this NOR gate. P is equal to S prime and Q prime. Now if we kind of sum everything up here, like I said, we need to simplify it a little bit because that of T and of T plus epsilon notation gets a little sort of unwieldy. So here what we'll do instead is we'll use Q to represent present state and Q plus to represent the next state. So we can rewrite our equations as Q plus is equal to R prime and S, or R prime and Q, and P is equal to S prime and Q prime. So here are our two equations, but don't forget, when we say a characteristic equation, we're really just referring to this Q plus equation. Okay. Now we can simplify it just a little bit further. Liam asks, so the present state equal to the next state if there is no change in inputs, or is the next state undefined? I'm trying to understand the question. So is the present state equal to the next state if there is no change in inputs, or is the next state undefined? If I understand your question correctly, no. So this equation always stays the same. Now you might get a combination of inputs and present state that lead to the same next state, right? Where really the next state doesn't change. But if you go all the way back to our original definitions here, I really got to click through everything so far back, right? For present state and next state, right? It's in the definition, right? So this present state is the state of Q output at the latch or flip-flops at the time any input changes, right? So the whole concept of next state versus present state is dependent on the fact that the input did change. So even if the input change leads to a next state that is the same as the present state, still technically it's considered a state change, and it's still governed by our characteristic equation. So let me just sort of chunk back through this. Now we can simplify our characteristic equation just a little bit, because we can take this and plot it onto a K-map. So we can simplify that characteristic equation by plotting it on a K-map. And if you take that and plot it on the map, you're going to get, 1, 1, 1 so let's see, a 1 at, S equals 1, R equals 0, Q equals 0. 1 here at, 1, and then at 4 and at 5. And then don't forget, if we lay it out in a truth table, right, all of our possible inputs, don't forget that S and R both equal to 1 are invalid cases, right? We're not allowed to have inputs for S and R both equal 1. So those get to be don't care conditions, and we can use those don't care conditions to simplify the expression, and we can get a characteristic equation that's a little bit simplified, that is this, where Q plus is equal to S or R prime and Q. So Q plus is equal to the set input or not the reset input and the present state. So here's our kind of final answer here. Q prime is equal to S or excuse me, Q plus is equal to S or R prime and Q. And then the last thing we can do is we can plot it in what we call a state table or a latch table. And that's going to look like this. So you might have multiple output columns that you care about, right? So here we have our next state Q plus and that present state P because we had two equations. But for now, just kind of ignore the present output P grouping here. Let's focus just on these two guys, right? On the left-hand side, you'll have the present state. So Q can be equals either 0 or 1. And then depending on the inputs, next state Q plus, you're going to get a different kind of output depending on the inputs. So we have a column for SR is 0, 0, a column for SR is 0, 1, a column for SR 1, 1, and a column for SR 1, 0. Notice that they're still given to us in gray codes, just like before. And then here we kind of look and see, well, what would the next state be if SR is equal to that value? So for example, if SR is equal to 0, then no change will happen. 0 will stay 0 and 1 will stay 0. By the way, these circled ones are states that are stable. So for example, if we go here, SR equals to 0, 1, so reset was set at 1. 0, so state is 0, state will stay 0. There's no change. But if the present state is 1 and SR is equal to 0, 1, that means R is equal to 1, which means that the present state is going to go to 0, so it's going to change from 1 to 0. And then let's see, if SR is equal to 1, 1, despite the fact that this is an invalid case, right, everything will go to 0, and we had a change from 0, or 0 stayed 0, or if present state was 1, then it changed to 0. But don't forget, that's our invalid case. That's the case that we don't like. And then finally, if we have set equals 1 and R equals 0, if present state is 0, then it changes to 1. And if present state is 1, then it just stays at 1. So this is the difference between we're going to call for now a latch table. Eventually, we'll call this a state table and a truth table, because now everything is dependent on present state versus next state. And then we do columns for our input values instead of rows. So this is how a latch table is put together. Are there any questions about this table? Okay, in that case, next up would be gated latches, but I don't want you guys to get ahead of the other section. So we're going to go ahead and call it, about 6 minutes early. And we'll leave it there. We will pick up with gated latches and then do the next lecture on Wednesday. And yeah, so if there's no other questions, comments, concerns, don't forget that you can get started on your project. Right now, it's due on Monday. And, pay attention to the schedule, and we'll kind of keep just chugging along here until we get to our first exam, or next exam. I keep going with the first exam. The next exam, right before our Thanksgiving break. So if there are no more questions, comments, concerns, thank you so much. And I'll see you guys on Wednesday. Thank you, Connor. You too.